Vale, venga, vale. Hello everybody and good morning. My name is Ana Martin and I'm going to talk to you about the digital analog quantum computational paradigm and how to use it to implement quantum algorithms. I am a PhD student at the Enquire group, and this is an investigation group that belongs to the University of the Basque Country, and here you can see all the people that form this group. I am going to start by telling you a little bit about the digital quantum computational paradigm, which is the most extended one. And then I will introduce the digital analog the digital analog quantum paradigm. And once I have shown you, espera un momento, me estoy poniendo nerviosa. Vamos a empezar otra vez, ¿os parece? ¿Qué? ¿Por qué?
Porque era la última. Hay una que es más reciente. Hay una que están los tres así, en vez de así.
Ah, vale, bueno, pues ya me la mandarás. Vale, perdón, chicos. Como he empezado, es que me he liado, no pasa nada, ¿no? Venga.
Hoy no.
Hoy no.
La semana que viene sí.
No me rayes. Venga. Hala, vamos allá. Ya, dale a play. Hello everyone and good morning. My name is Ana Martin and I am going to tell you I'm going to talk to you about the digital analog quantum computational paradigm and how to use it to implement quantum algorithms. I am a PhD student at the University of the Basque Country, and I am part of the Enquire group, which is formed by all of these nice people that you can see in the picture. I will start my talk by introducing the digital quantum computational paradigm, which is the most extended one, and then I will transition it towards the digital analog computational paradigm, which is the center of this talk. Once I have explained how does it works, I will introduce you how to use it to implement long-depth quantum algorithms, such as the quantum Fourier transform or the Harrow-Hasidim-Lloyd, the HHL algorithm. And after that, we will compare how do these both paradigms behaves under the existence of experimental error noises. But first, just for being in the same page, let me tell you what I mean when I speak about computational paradigm. I refer to the criteria which is behind the implementation of any algorithm into the actual device, and attending to the building blocks that this paradigm employs. We can be speaking about the digital quantum computing or the digital analog one. The digital quantum computational computational paradigm is the most extended one, and the building blocks that they use to change the state of the qubit or to create superposition are digital pulses applied to one concrete qubit. That way they create these single qubit gates, and in order to create entanglement, they apply digital pulses simultaneously to both qubits. So they create the two qubit gates. Using this paradigm, it's possible to achieve high fidelity rates whenever we want to implement short-depth quantum circuit in these devices, and there have been relevant contributions in different fields such as quantum machine learning, finance, open quantum systems, so on and so forth. The drawbacks of this paradigm is that as the depth of the algorithm increases, so does the resources we need to implement it, and although experimentally single qubit gates present low noise rates, the two qubit gates does present significant noise rates that accumulate along the process. This is due to the crosstalk between the qubits of the system. There is an error that appears whenever we activate and deactivate these gates, and although this can be overcome by applying quantum control techniques, these techniques are not scalable. So whenever we have a long-depth quantum circuit or a big quantum computer, we cannot use these techniques to solve these problems. But maybe changing the paradigm can help us. So since quantum control techniques are not scalable, we are still facing this crosstalk interaction, and we propose to see this this way. What if instead of trying to minimize the crosstalk interaction among the qubits that is going to be present already, we try to use it as an additional resource to implement our algorithm? And that is the main idea behind the digital analog computational paradigm. This paradigm combines digital steps of fixed time performed by digital pulses, so the single qubit gates that I mentioned at the beginning, with analog blocks that are analog blocks of controllable times that are performed by the evolution interaction of the Hamiltonian that is already present in the quantum processor. That way, this paradigm creates entanglement and superposition and changes the state of its qubits. And thus, the digital analog paradigm combines the flexibility of the digital computational one and the robustness of the analog simulation. It is possible to use this paradigm to simulate different interaction Hamiltonians, and the most easy one to show how does this work is the inhomogeneous all-to-all two-body Ising Hamiltonian, and I want to use this interaction Hamiltonian without losing generality to tell you how does this paradigm works. So as a resources, we are going to use the interaction Hamiltonian. We are going to assume it is a homogeneous Ising Hamiltonian. This is a good approximation since this is the Hamiltonian that naturally appears both in transmon qubits this is the interaction Hamiltonian that appears either in transmon qubit or whenever we have a spin-spin interaction in trapped ions. And the other resource we are going to use is the digital step is single qubit gates, so unitary rotations around the x-axis. Our goal is going to be simulate this inhomogeneous Hamiltonian, which is an all-to-all two-body Ising Hamiltonian of arbitrary couplings, as I mentioned. So by slicing the homogeneous time evolution into at most that amount of analog blocks of different time lengths, and then sandwich that slices by single qubit rotations, the problem reduced just to find an appropriate map between the time of the slides and the total amount of time of the simulation Hamiltonian, simulation unitary that we want to implement. So in the end, the whole problem is reduced to a matrix inversion problem that has a unique solution since the matrix that map both times is invertible. What I have described here is what we call the stepwise digital analog approach, where the interaction Hamiltonian is sandwiched between the digital blocks. So we start by applying digital pulses on single qubit gates, on single qubits. Then let the system interact during a certain time, which is the time slide that we have calculated, and then apply the single qubit rotation in the same qubits that we have done. And we do this, so on and so forth, until the very end of the process. The result that we obtain by using this approach is equivalent to what we would have obtained if we have used the digital quantum computational paradigm. So the solution is exact. But this switch on and off, but switching on and off the interaction between the qubits can introduce some experimental errors that accumulate during the process. So there is another way, there is another approach that can be taken when we use digital analog, which is the bank digital analog, where we turn on the interaction at the very beginning of the process, and we don't stop this interaction until we are finished. And the single qubit gates are performed on top of this interaction. So the system starts interacting, and without turning it off, we apply the single qubit rotations on top of the interaction. This way, we are introducing a digital error that doesn't respond to experimental noises. It's just the result of the superposition of the Hamiltonian that comes from the single qubit gates and the Hamiltonian that comes from the interaction blocks. But these errors scales much better than the experimental errors that would appear both in the digital and the stepwise case, since the time that it's taken since the time that a single qubit gate takes to be applied is much smaller than the time that the interaction takes to get stable, to be stable. So using this paradigm, it's possible so we can use this paradigm to implement different quantum algorithms. All we have to do is to express the unitary process in terms of an interaction Hamiltonian, then find the appropriate map between the time slices and the simulation time, solve the inversion matrix problem, so that way we can know the duration of each time slide, and apply the protocol. I'm going to show you how to use this for two relevant examples, which are the quantum Fourier transform and the HHL algorithm. The quantum Fourier transform, this is the digital implementation that it's easy to be found in any quantum computing book, such as the Nielsen Chuang or any other quantum computing one. The unitary matrix that expresses the whole process can be expressed in terms of single and 2-qubit gates. And what we have done is to engineer the Hamiltonian in order to express it in terms of an inhomogeneous all-to-all two-body Ising Hamiltonian. That way, we can use the protocol that I mentioned before to implement it using digital analog techniques. Here is a simple example of 3-qubit. This would be the implementation, the digital implementation, single and 2-qubit gates, and by expressing its blocks by the unitary of the process, and then the unitary of the process by this all-to-all two-body Ising Hamiltonian, we can use either stepwise digital analog or bank digital analog to implement the whole operation. If we take into account no error, no experimental noise, we could expect to have exactly the same fidelity whenever we apply both the digital and the stepwise implementation. We achieve 100% fidelity when we apply this quantum Fourier transform, for example, to a family of states. But as you can see, the bank protocol, the bank DAQC protocol, has an inherent error that makes it different from the exact solution. The fidelity is not much different, but of course, as we increase the number of qubits, we get worse fidelity. I will show you later on that whenever we introduce experimental errors, this figure turns over, and the better fidelity is achieved by the bank protocol instead of the digital or the stepwise. But before I do that, I will tell you about the other algorithm that I promised I will tell you about, which is the Harrow-Hasidin-Lloyd algorithm. This algorithm, what it does is just solving linear system of equation, and in essence, solve any kind of matrix inversion problem. The runtime of this algorithm is polynomial in the logarithm of log n, which n is the dimension of the problem matrix A, and this is exponentially faster than any other classical algorithm. It can be divided in 3 subroutines, which are the quantum phase estimation to compute the eigenvalues of the problem matrix A. The second step would be the ancilla quantum encoding, and we do this to store the inverse of the eigenvalues. And finally, we have to reset the register back to 0 in order to be able to measure just the ancilla one, the ancillary qubit, and we do this by performing the inverse phase estimation. At the same time, the phase estimation can be divided in 2 subroutines. The first one would be a conditional Hamiltonian evolution applied on the memory qubits. If we assume that the matrix problem A admits an m-body decomposition where m is much smaller than the logarithm of the dimension of the problem matrix, it is possible to upload this matrix efficiently using different digital analog techniques that are together in this work that we made some years ago. And the second part of the phase estimation is just apply an inverse quantum Fourier transform, which immediately follows from the direct quantum Fourier transform that I have presented previously. The next step of the HHL is to perform an ancilla quantum encoding. First, we have developed a systematic way to digitally implement this part of the algorithm, and this is possible to be done by any kind of problem matrix A. We don't have any previous information of this matrix. As you can see, there is an exponential number of multi-qubit gates that prevent us to implement this using current devices. So what we have done is to analyze how the unitary of this process is expressed. So we have analyzed the whole unitary, and we have expressed it in terms of its Hamiltonian, and grouped the Hamiltonian terms by the amount of body that are involved in this operation. So we have 1 body terms, 2 body terms, and 3 body terms, and they are presenting the ancilla quantum encoded part, the whole part. After analyzing how each of these terms behaves, we have seen that the leading terms of this Hamiltonian are just the 1 and the 2 body terms, since they converge to a constant value plus some other terms which are of this order. And the last part of this Hamiltonian, the 3 and more body terms, they decrease exponentially with the number of registered qubits. So this gives us the idea that we can apply an approximate version of the HHL by getting rid of those terms and assuming a controllable error, that we are going to call epsilon, which decreases exponentially with the number of registered qubits. So in the end, instead of having an exponential amount of multi-qubit gates, we are only focusing in the gates that represent the 1 and the 2 body terms interactions. And as you can see, this approximated ancilla quantum encoding Hamiltonian is an inhomogeneous two-body Ising Hamiltonian. So we can simulate it using the digital analog techniques that I have presented at the beginning of my talk. So all in all, the HHL algorithm would be digital analogically implemented by dividing it in different steps, as well as we have done it for the digital case, and use different digital analog techniques for simulating each step. But now I am able to show you how this paradigm behaves whenever we have experimental noise sources. As I have told you, is it possible to expect that the error is going to scale up better in the bank digital analog protocol? And we have done some works on this issue. We have performed the quantum Fourier transform on the same family of states as before, for the case of 3, 5, and 6 qubit, and we have introduced several sensible noise sources. We have run this simulation for both paradigms, and we have gotten the following results. The family of states that we have taken into account is the same one, so a linear combination of W and GH set states. And we have introduced both sensible experimental noises, such as the magnetic field noise, a Gaussian phase noise whenever we have a 2-qubit gates, Gaussian coherent noise for each analog block. And also we have included incoherent noise sources such as the measurement error, the bit flip, the coherence, and thermal relaxation. By measuring the fidelity between the ideal and the noisy implementation, we can see, let me focus on the worst case scenario, which is 6-qubit system. We have seen that both the digital implementation and the stepwise implementation has lower fidelity than the bank digital analog implementation. And this repeats for the other cases. When we have a 5-qubit system, the best fidelity is achieved by the bank protocol, and so it does for the 3-qubit system. This is due because this is produced because the error that it's introduced in the digital and in the stepwise method is going to be accumulated along the whole process, whereas the bank method only includes this whereas the bank protocol has this error that scales up better with the number of qubits. So to sum it up, ¿cómo voy de tiempo? Ay, Dios mío, 18. Pues voy lenta. To sum it up. So we have seen that current devices suffer from important noises that prevent us to use it to implement long-depth quantum algorithms, and we propose digital analog quantum computing to overcome these experimental limitations. The main idea of this paradigm is to get advantage of the inherent interaction between the qubits instead of trying to minimize it. And that way, we are able to implement long-depth quantum algorithms, such as the quantum Fourier transform or the HHL, and has better resilience under noise sources. These results show that digital analog quantum computing is a valid alternative to implement, to keep developing the field of quantum computing using current devices. Here you have a compendium of all of the works that we have done in this digital analog topic field. And with that, I conclude my talk, thanking you for your attention. Probablemente os hayáis dado cuenta, pero estaba muy nerviosa.
Multa por exceso de velocidad.
Ay, Dios mío. Te he visto decir que no, Miquel. Te he visto que has hecho...
I have.
Yes.
Well, the other day, in the other talk, in the introduction, you explained in more detail the idea of digital analog.
Vale.
And you put an example and how the pulses are changing the inherent dynamics of the system.
These things, you mean like me?
Yeah, this example for a few qubits, just for 2 or 3, I think that it makes more intuitive what you are explaining before that, saying that you have a matrix that you have to invert to calculate all the times. So
okay.
To me, the other day, it was easier to understand what the digital analog is in essence. But it is a perspective, a personal perspective.
Okay, I wasn't sure if letting it, keeping it, or taking it away. I wasn't.
Time enough to explain it.
Yeah, I can see now. I can see.
So I don't know if explaining this in detail for a trivial example is something that makes the explanation easier to understand.
But for me, it depends on the. So as you are short in time.
Vale.
Because today the concept of understanding it was like quite fast. You went quite fast through the explanation.
Also the metrics of this. In the next slide.
No, I don't have.
You can also introduce
all I have is this.
Like this is like what I miss.
Okay.
This is like basically.
Vale.
And also I miss your works, the reference to your works during all the presentations.
Ah, shit, maybe. Yeah. Oh, esto no es. Vale, okay. Sí, it's true. I didn't. In fact, while I was rehearsing it, I thought, shit, what is my reference? So, yeah. Sorry, yeah. A ver, un momento, I'm going to. No se ve, ¿no? Okay, thank you, Javi. No, keep, please.
Yes.
No, sure.
Yeah, because it is quite a large talk. I would recommend you to stress the points in which you have to stop, breath, and begin with a new point. For instance, when you speak about the HHL, it seemed that everything was continuous and at the same level, but you have to say, here we are in one of the highlights of the talk. So stop if needed, take a break,
and begin with that and stress the important, the relevant points of the talk.
Okay.
I have some things. First, in the first part, when you are explaining everything, like the paradigm, blah, 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 I felt like the slides were too full of text.
Okay.
I think it's a bit difficult to follow. So I would suggest to
These
maybe
ones,
add
these stuff.
some images as you do next, that you put these blocks with the single cubic gates and so. I think that would help.
Vale, okay.
Yeah. And yeah.
Like better this way than that this way, or what? Ah, no, claro, tú no lo
I am not
ves.
seeing it.
Yeah. So
Yeah,
you
it
mean
is-
these ones?
Yeah, when you
But-
maybe say digital, maybe you can put a little circuit and then in the
Okay.
digital analog some block.
Similar as I do here, or what do you mean?
Here there are no photos.
No, but it's
But
not
there's
automatic,
side-
Yeah.
It helps.
Yeah,
Okay.
yeah,
Vale.
yeah, I meant like some figures. And then there is a little detail. I think you say to perform 2 cubic gates, you have to apply 2 pulses on 2 cubics.
No, I don't know what I said. I meant that you have to apply the pulse at the same time to 2 qubits or something like that.
But
I don't know what I said.
No, if that's true. When you do the crosstalk gate, I think you only have to apply a pulse to 1 of the cubics, right?
Okay, vale.
Just a little part. Yes.
Yeah, okay.
Yeah, and finally, for me, the figures in which you speak about the errors of the different ways to do the things, I was quite confused. For
What-
me, it was really difficult to follow. I didn't know what was what.
A ver, what do you mean this or the next one?
No, yeah, exactly. Like that, I don't know what I am seeing.
Colors are not
Yeah.
easy to
Yeah.
Green,
Uh,
blue, black.
maybe
I don't know if I can change it because it's from the paper. The simulation were done in MATLAB by a master student, and that code is.
You
Make
have
them
the-
appear step by step, maybe. So this is the case
Yeah.
for
Yeah.
these qubits. These qubits.
I try to. I mean, I cannot
Yes,
modify
but
this
the color is
thingy.
difficult to.
I try to do this with
No, but
this
you
Yeah,
can
color.
put a square, a blank square on the image so that you hide the lines that you don't want to appear.
Okay, I think it's kind of difficult since they.
We are.
Yeah. But maybe I can try.
Yeah, and the same for the first one. The first one for me was even more confusing.
The first one, the first one. The no
It
noise
was
one.
the quantum Fourier transform. Or
This one?
something, or phase
yeah,
transition.
exactly, because you didn't say what you were talking there.
Ah, yeah.
There are crosses, lines like that, and then suddenly colors. I don't know.
Okay.
Mhm.
Okay. The type of line mentioned the protocol and the color, the amount of qubits, but I didn't say. it.
Yeah, but I didn't.
You didn't even say what you are representing there.
I thought that it was like smooth transitioning, but I see that it's not smooth and not transitioning. Okay. Okay.
And but
Yeah, I didn't mention on purpose, but I thought that it was clear enough. But maybe it's only in my head. So okay.
Transitioning from what to what?
From the previous
To say that if we take no noise, no experimental noises into account, the fidelity that we could get
Yeah.
could be this one, like digital stepwise exact and the band different.
But between this slide and the slide that you compare them with noise, there is the whole HHL path.
Yeah.
So there is no transition there.
No. The transition I meant between this one, digital analog implementation of quantum Fourier transform, and how would each circuit look like if we take no noise. But maybe it's confusing. I don't know.
Then you have time
Yeah.
to explain all.
Vale.
the full errors you show after, I mean, when you consider experimental errors, it's only for the HHL, right?
No.
Okay.
Okay, maybe it's not clear at all. In fact, when I take into account the errors, this is from when we implement the quantum Fourier transform.
Then maybe it
It's
would be better to put it after the quantum Fourier transform. I don't know.
But then how do I connect it to, okay, and now I will tell you about the HHL. My idea was to digital analog could be used to quantum algorithms like blah blah blah, and the resilience under noise is this
You
one.
have to say that this is the new result. The HHL is what Javi was telling you.
Yeah, that is
To
true.
Make it to highlight which are the important things, the new things, and the most important things.
Okay.
So I think now the structure that you have followed is start talking about what the standard digital paradigm is, and then you introduce the digital analog part, and then you start introducing the algorithms that you have implemented with the digital analog part. And you start like with a way down, introducing the quantum Fourier transform, and then plotting those the figure that we have commented right now, where the bank digital analog is the worst one. So that's like a way down, stating that your solution is not so good, and then you go up explaining that, okay, but if we include noise, our approach is better than the others. But you could change the idea and use a way up, introducing the problem with the quantum Fourier transform, then this as a successful case where introducing noise makes your approach better, and then the HHL as a future perspective of what can be achieved with the digital analog.
Okay, I
And
like
that
that.
way you can stress.
Yeah, I can stress out both things and claim the HHL thing like HHL. Yeah,
Like
maybe
we
that's.
can be, and maybe for this it's
Yeah,
useful.
maybe, yeah, that's a good idea. Because the other tag, the HHL, in the last part was like, okay, and now HHL, let's go.
Yeah.
I don't want it to
But
be
we can do
like,
that, like,
Yeah, I like
now
that.
there is, this is the most important thing, incredible, latest, new.
Firework.
okay, I need to write that down.
So there is no way to build a graph like that for the HHL, of course not for the next week.
Of course, not for the next week.
But I mean, you have intention to do
I would say
something like
no.
that.
I would say no for this paper.
Not for this paper, of course. I mean, but
Uh,
if there is the intention to build something like that, it would be interesting also to say why do we expect those results also for the HHL.
no sé qué está haciendo.
Like the results for the 90 days.
Yeah, no, but that figure it's not easy to get. I wouldn't say it. Yeah, no. No, porque me muero.
No, claro, es que
But you expect similar results.
Yeah.
You don't know.
No.
You-
I expect them. I mean, it would be nice to have that simulation, but I think it's.
No, it's not for this paper, but my main problem, everything is always the same. From your talk, I don't see the motivation to use the AQC.
Okay.
This is so because you are not making it clear, but crystal clear. It's what if you do this, all the rest of the talk follows automatically. Because now you
So
are
stress out the fact that we can implement long-depth quantum algorithms with better better
why
rates.
is the reason for you? Why? So the intuition, the physical intuition of why you can do it.
Okay.
And suddenly, so the noise is playing a role that is coming from nowhere. So initially, when you are explaining everything, there is no noise in this explanation. But
Okay.
afterwards, after the quantum Fourier, you say, it performs worse because you have learned. And then you, as a thing, and then you say, no, but if you introduce errors, other than an error for the digital, then it performs better. But how?
Yeah.
What's this intuition?
Anna usually says that something like interaction is not a problem in producing crosstalk, but a resource. Is that true?
No, this is the another problem.
But I have
This is what I
changed
say no.
But I have changed that. So
you-
I said instead of minimizing it, use it as an alternative resource or something like that. I say I no longer say that.
But the real
Isn't it true either?
No, it's not that this one. It's not the crosstalk. Crosstalk is a way to talk in quantum computing, nothing else. It's not the. But the idea is that if you have a quantum system, this quantum system has an interaction, natural interaction in general. Could be Heisenberg, could be Ising, could be whatever it is. The interaction there. And then what you do normally in digital is to try to modify it in order to put some digital gates and decompose it. But in order to do this, you have to switch off plenty of interactions artificially that they are present there, and this doesn't work very well, and this produces errors. However, it's not necessary to do this. You can just keep it everything on and do the dynamics on top of that. And this is what digital analog makes.
Vale. Okay.
So,
And
then when you introduce stepwise and bank everywhere, you should say, okay, the bank is introducing this error, but when you introduce the rest, but you avoid to switch on and off these interactions or interactions with the system, that you can connect with the previous thing that you set when you are introducing the digital analog. And then when you are displaying the bank, you say, but here you still have the same problem because you have to switch on and off. So the idea, or the natural idea, is to keep everything on and make the single period rotation on top of that. This introduces an error, but when you compare, put in balance the error coming from switching on and off and this error, this scales better. So for me, this is the natural way to explain. And you can do this instead of so many text as they were saying, with images, so pictures in fact of things.
okay. But mention bank when I speak about the drawbacks of digital quantum computing, like this, turning on the 2-qubit gates and then turning off, crosstalk, blah, blah, blah. Just mention it, but not introducing digital analog. Still, I have to do this.
So the point is that, so the idea is that in digital, so in a quantum system, the interaction is that you have to switch it off in order to perform gates. If you want to compose everything into 2-qubit gates. So the most logical thing is why I should do that. This is not crosstalk. This is in quantum interaction. The crosstalk comes from the language of quantum computing, where you are trying to perform a 2-qubit gate, and this 2-qubit gate is actually affecting the qubits around. And this is called crosstalk.
Okay.
But in the paper with Dacio, you use the idea of crosstalk, or you call this crosstalk part. I don't think that this is the most natural, especially if in the audience you have people who are not from quantum computing. This will sound weird.
Vale. Okay, I like that way to put in it.
And there is not crosstalk, it's cross-resonance.
It's
They give to
it's cross-resonance. Actually, it's true, but this is very, very focused on superconducting circuits. And there is something that you are missing also, which is hyper important. Which is the experiment from Yang Wei Fan. He's giving you the back of that this is experimentally feasible and super interesting, and you are missing that.
Es verdad. You're right.
So they are doing the experiment with 60-something qubits and digital analog, and you are missing this part, which is
vale, venga, es verdad. Where should I put it?
at the end. So it's not necessary. This is a little bit unclear, or at the end or at the beginning. But I say that at the end will be better.
Okay.
So after saying that you have HHL, and you can say, okay, this algorithm scales quite. You need a lot of gates and so on, and a lot of qubits in order to make things nice. But experimentally, we are going in this direction. We have experiment, blah blah blah.
Vale. Vale.
Okay, I have one question.
Yeah.
So from the unexpected on the digital analog concept. So when you start to talk about the bound control and other things, it reminds me a lot of things about this quantum optimal control. So I don't know whether it is necessary to mention this direction. For instance, when you switch on off the interaction and the bound control, it will remind other people to think whether this digital analog is relevant to the quantum optimal control or rocket engineering or other things. I don't know whether you should put one or two, one slide or just mention or compare or benchmark the advantage. It seems that you are scaling the digital analog when you list all the papers.
Yeah.
But when you start from this 1 or 2 qubit or other things, it can remind that this is the quantum optimal controls, right? And whether For instance, the people were designed, for instance, like adaptive or optimal control. Like switch off or control the amplitude or the duration of the optimal control process. I don't know whether it is useful for this design of digital analog things. And it reminds me a lot of things relevant to around this direction.
Yeah.
So I don't know whether you should modify this. Okay, you see my point.
Yeah, I see your point, and I see a drawback in myself, which is I don't know a lot of things about optimal quantum control. So if I introduce it in the slide, if someone pointed out and asked me anything further than what I have started for the presentation, I don't know. Maybe you can help me to.
When you show the one slide, I think that one slide single qubit. I didn't remember, but anyway. So
I don't know.
The other side then about this bounded things. Then immediately one question will appear. Whether this is relevant to the all-around optimal control theory or to design this digital bound process, something like that.
Yeah.
So you can do it in the conclusions and outlook, because you are missing a little bit of outlook for the next
What
steps.
I have missing what?
An outlook. So
yeah, see.
The perspectives of the field.
Yeah.
And there you can introduce that a good point will be to use quantum control techniques in order to enhance some of the noise, for instance, in order to reduce the bank error and things like that.
Vale. Vale. Okay. Thank you. And maybe you can help me later on what else would you expect from there to appear, because I am not an expert in that field at all.
Yeah, check one paper about the one paper in physical review X quantum. Then a future review article about quantum control, and also one paper from the leader. They are talking about the quantum control enhance this digital process from the classical to quantum. Yeah, check it.
Vale, okay. Well, maybe you can give me the reference later, because it's not going to be possible. But, I mean, few time, a lot of things. But yeah. Yeah, maybe you can give me the complete reference.
Then there are a lot of experts on that.
Yeah, I know. No pressure.
In the HHL, you are missing the code. I think this will be very good. And to type
Yes and no. Because I didn't know whether I was going to have time or not. I have the slide, but I didn't know if I was going to have enough time to present it and how to put it. But if I introduce the HHL the way you mentioned, it's much more natural to introduce this co-design architecture.
I think at the end of you can say one of the outcomes. So this one, by the way, you are missing in the HHL to say that it's approximate. That's a very important thing.
I mentioned it, but not enough.
Maybe I was writing comments in the meantime, so I missed it. But it's important to say that it's approximate and with the controllable error. But the last slide or after the HHL could be the code.
Vale. At the beginning it was intended to be included, but I didn't know how to link it, but I think in this way it's better. Okay. More comments?
I have one comment about the HHL slide where you compare the digital approach and the digital analog.
This one?
Yeah, because I think for someone that is used to work with circuits and so on, it might be strange to have blocks also acting on the first qubit. So I think it's a good opportunity to remember that when you're doing digital analog, you are feeding the interaction Hamiltonian on all the system at the same time. So you cannot turn off some part of the circuit and do no other thing. You have to work with the whole system Hamiltonian.
Okay, maybe I can stress that. I think.
It's just one sentence, so to remember the point that you
I mean,
in the beginning.
Yeah, maybe. When I introduced the digital analog, I also put this whole block thingy. Like, bueno, ahora van a empezar a bailar los qubits, but this, like, it's
Yeah, so to recap on that.
okay.
and
Yeah,
to-
maybe.
Yeah.
Okay, that would be useful. Yeah.
I have one curiosity. It's not. It's just a question for me, for myself.
No ta question, but a comment. Okay.
Yeah, no, it's a question. The thinking of the young way pan guy. So he did digital analog. So they had like a special circuit which had the interaction always on. It's different
think
of
so.
the IBM guy.
You don't need to change anything. Only thing that so if you have two qubits connected, if you want to make to switch the interaction on, you have to put one or two and to add the driving in one of the qubits in order to put this qubit of red.
Yeah, you have
They are-
to do the thing of the Casio's paper, right? Yeah,
In which sense?
in Casio's paper you put the crosstalk resonance condition always on, right? And you will be
Exactly.
digital analog way. This is what young way pan did, or did
Yes,
they
but
build
you don't need to construct anything with any system. You can
But I mean, I can imagine that you can build a circuit in which that interaction is always on and you don't need a driving.
Yeah. If you, well, more or less, because when you try to construct a qubit and you want to reproduce this qubit, the accuracy is usually not very good.
You want to reproduce?
Reproduce a qubit, right? So the capability, the experimental capability that we have now to reproduce a qubit in the way that we want is not so good
Okay.
in this moment. It's better and better with the time, but it's still not good. So there is always an of resonance between the people. So you can still, by external control, put them even better in resonance and to enhance the interaction. But you don't need to change the protocol for anything. It works. Well, except for the people with the technology which is called that they have control. They put qubits between the qubits, and they use this qubit to put off resonance in order to reduce the crosstalk. That is what the IQM was doing for the technology. And in this case, just the opposite because you are reducing a lot the interaction between them. But for the rest, they connect directly. It doesn't matter which kind of interaction, or if it is inductive, capacitive, whatever kind of interaction.
I just wanted to know if they co-designed the circuit in order to do.
No, the co-design is not this one. The co-design consists in designing which qubits are connected to which qubits in order to reduce maximum the number of subqubits that you need. So this is the reason why Anna has this guidelines.
Yeah, I have also a paper on that. But I have seen papers in which they do change they do design the circuit parameters so that the interaction is not like dampened, because in IBM's computers the natural interaction is really low, so you can't do digital analog as like this. But there are other superconducting circuits that uses the same kind of qubits, like Krasnov qubit, but where they don't want the interaction to be low but high, and you can design that. And I think that in this paper, they design the circuit so that that interaction is not so low. Because if it is low, you need a really low.
But you can have the high, you want to have high.
Yeah, and that's why you have to design it. So that's why in IBM you cannot run.
You can do digital analog with any, independently if it's small, it's slow or fast interaction between qubits. What you need is that the single qubit control is much faster, independently on which it.
There is,
Yes.
there is.
Yes.
If the interaction is so low that you have to have a really long time to apply the interaction that you want. For instance, quantum simulation, you need, if you have really low resources, you need a really long time. If you have really long time, your qubits will go here.
What? No, it's not in this way. So what you need in order to perform digital analog is to have a single qubit control faster than the 2-qubit interaction, much faster than 2-qubit interaction. And of course, the depth of the circuit that you will be able to apply depends on the P1 of your system, but it's something independent of that. So the longer you need, yes, we can, of course, yes, we should. So yes. So the time, the coherence time of your system is what allows you how much time you can apply your algorithm. Nothing, not related with digital analog at all. Digital analog or digital, the limit is the same for digital. You perform the single thing gets slower, worse,
Vale.
you can apply less days.
Aquí, o sea, digital analog is not limited by single qubit, but mostly because of the interaction time. What you need.
Oh, well, as you will.
I found a little bit confusing that the styles for the lines that you chose for the plots of, when you compare the digital and stepwise and the line
Yeah.
were different.
Yes, because they are from different papers.
Yes,
But
I found it a bit confusing because the boundaries in one is a solid line and then in the other it's a dash dotted line.
yeah,
But I mean, it's not, it's just
here.
OCD.
Yeah, and in fact these colors are so difficult to differentiate, I think.
Yeah. You don't have the cheap. No, but the line styles, I mean, are, you can appreciate that they somewhat they are in different.
But do you have the so not to run it, but the source in the MATLAB? If you have the MATLAB code,
Es que I think she did this using Python. If I had the MATLAB.fig, that would be great. But I think it's in Python. I will look it up and maybe I can change it because the colors and
but
stuff.
Python is not vectorial. I don't know.
But if I maybe I can run the codes, but some issues.
But the plot is
the figure is a .png.
no, but my question is if the outcome of the plot in Python is a vectorial plot or not? Because if vectorial, normally you can manipulate exactly the same answer.
I think if it's PNG, then it's not vectorial.
PNG.
PNG, yes. So it has lost all of the things that I can show. It's a picture, like.
Okay.
I can try to look it up and maybe run the codes and change the color.
I think it's easier. You can just plug it into GIMP, and in GIMP you can change the colors of things. It's look some tutorial and you can change the color manually. It's a little bit of work.
Everything is a little bit of work. I will try to do something about this because it's raising a lot of problems. Yep.
You can just put like white boxes and that.
Yeah, but the thing is that here they cross. So okay, yeah, I can play with pixel.
Yes, I think it's the easiest thing to do is to hide the length using maybe with boxes and ellipses you can do.
There is another way maybe. If you put the formula down of the family of the shape and the legend on the left, maybe you can increase the size of because the problem is that the density of lines there. So you
But I think it's going to be even worse because not worse but the same since the lines are thick. So
no,
it's just going to be bigger.
Have a big, with the density of light, not the same. Having that like that or having half of the slide.
Or maybe I can try to, I don't know. I mean, if I had just this part, this 6 qubit simulation, would it be enough? I mean, I left everything because I thought that comparing with the rest of cases might be relevant, but if it's not going to be even relevant, then I can try to erase everything or try to run at least just this one. I don't know. I mean, I thought the arrow helped, but I see that it doesn't.
Yeah.
Okay. And it moves, it's fancy. But okay, I am going to try to do something about this picture.
But yeah, make it even larger layer.
Yeah, okay. I mean, don't forget it's a PNG. So I'm going to do like zip, and the pixels are going to do zip. So maybe it's even worse.
Well, the idea is a pseudo vectorial
Like,
type of PNG is a pseudo vectorial. It's not it's better than the J.
now it's bigger. Do you think it's clear? Now it's bigger. Do you think it's clear?
Yes.
Really? Really, I see the same shit.
Yeah, because you are right.
Next to that, next to
Screen. Because you are right.
Okay. Okay.
Duplicated light. Duplicated.
Yeah, I have done that. Yeah.
Anna, keep in mind that the place in which you are going to give a talk is 5 times this. So imagine if you are at the end of the.
Well, that means
Ay, Dios
the
mío.
important thing is to say it correctly. They won't see the slides.
And they are old
It will be
people.
also bigger, but
A ver.
that they are quite far away, is what I mean.
Wow, excellent.
Okay, I try to do something about it.
Maybe you can ask for another person.
Vale. More comments, guys? I will apply all of the changes, rehearse it more times, not be so in order not to be so nervous. And I would appreciate if you listen to it once again, maybe tomorrow, something like that. And also Tasio has to present, so maybe if you want, and I assume that you want, and if you don't mind, you can show us both, see us both.
We can do it together because